Hello everyone. In this video, we will work out the review problems for the upcoming midterm exam. So the first problem over here is asking us to convert these decimal numbers 124 and 421 into binary. So let's use the division method to accomplish this, and let's get started with 124. So recall, we will simply keep dividing this number with 2 and keep track of the remainders until this number reduces to 0. So dividing 124 by 2, we get 62 over here, and the remainder is 0. Go on dividing in this way, goes 31 times, the remainder is 0. This goes 15 times with the remainder of 1. Again, continue like this. So here we are left with 1, which goes 0 times, and the remainder is 1. Now these remainders we will read bottom up, and that is our answer. So the answer over here is basically 1111100, which is basically the same as this number here. We can similarly translate 421 into binary number. Once again, let's start with this number and go on dividing it by 2. Keep track of the remainders and read bottom up finally. So this 421 goes 210 times, the remainder is 1. I keep dividing. So here is the division. Let's read these remainders bottom up. Once again, the answer is basically 110100101, which is the same as the number over here. So the next problem over here is asking us to translate the given binary numbers into decimal. So recall that every digit in a binary number represents a power of 2. So starting from here, this is 2 to the power 0, this is 2 to the power 1, this is 2 square, and so to get the decimal number, we essentially need to multiply these powers of 2 with the corresponding binary digit in that position and add up all these products. So essentially the zeros will not contribute anything to the magnitude, because 0 into anything is 0. So we simply need to sum up the powers of 2 that correspond to a 1. So for instance, 2 to the power 9 over here, 2 to the power 4 over here, 2 square, and 2 to the power 1. So that is the same as 512 plus 16 plus 4 plus 2, 534. Exactly the same procedure can be followed to compute the magnitude of the second binary number over here. So let's start by listing the powers of 2 for each of these digits in this number. Again, we just need to add the powers of 2 that correspond to our digit 1. So basically 2 to the power 9, 2 to the power 7, 2 to the power 5, 2 to the power 4, 2 cube, 2 square. So this is the same as, again, 512 plus 128 plus 32 plus 16 plus 8 plus 4, and adding all of this we get 700. So this is our final answer. The answers to the conversion question are also listed over here. This question over here is asking us to translate the given hexadecimal numbers into decimal number. Now this translation is a two-step process. The first thing we do is we translate these hexadecimal numbers into binary, and then the second step is to translate the binary number into the corresponding decimal number. So let's start with hexadecimal ABC. So recall that A is basically 1010, B is basically 1011, and C is 1100. So this is our binary number corresponding to hexadecimal ABC. Now again, using the powers of 2, we can translate this binary number into the decimal number. So the corresponding powers of 2 are listed over here. Let's now add the powers of 2 that correspond to a digit of 1, because 0 multiplied by anything is a 0. So zeros won't contribute anything to the binary magnitude. So we get this sum of powers of 2, and let's write down the corresponding numbers. So 2 to the power 11 is basically 2048, 2 to the power 9 is 512, 2 to the power 7 is 128, 2 to the power 5 is 32, this 2 to the power 4 is 16, 2 cube is 8, and 2 square is 4. If we add all of this, we get 2748. Similarly, we can translate this hexadecimal DEF to the decimal number. So let's quickly translate this into binary. D is 1101, F is 1111 and E is simply 1110. Listing the powers of 2, we get adding the powers of 2 with the digit 1 gives us this series over here, which is the same as, when you do the math, all of this will add up to 3582. The answers are also summarized over here on this slide. Now here is a sample question related to computer level hierarchy. Recall in the class we talked about a 6-level computer hierarchy, where the topmost level was the level representing the high level languages like C, C++, Java and so forth. And we saw in the class that the code is translated level by level from level 5 to 4, 4 to 3 and so on, and eventually at level 0 the true hardware of the machine executes the code. So this question is asking us what system software or hardware translates the code from level 4, which is basically the assembly language level, to level 3, which is the operating system machine level. So recall, compilers are responsible for translating the high level language code into assembly code, and it is the assembler's job to convert or translate the assembly code into the machine code. So the answer here would be an assembler. Alright, so the next question is asking us to translate this given C++ code into equivalent ANA assembly code. For this question, we are going to assume that variables A, B, and C are allocated in registers R2, R3, and R4 respectively. So let's first initialize A, B, and C to 1. So that's pretty straightforward. We say LLI A is in R2, so we'll say LLI R2 1. So this is simply saying A is equal to 1. Similarly, we'll say LLI R3 1, so which is basically B is equal to 1, and then we say LLI R4 1, and because C is stored in R4, this basically means C is equal to 1. Now note that this do while loop, it runs 5 times, or basically we have to make sure until A is less than 5, so this basically goes 4 times. So to do that, to keep that loop counter, we'll initialize another unused register, let's say R5 to 5. So this is our loop counter. Now let's get inside this loop body. So this addition, note that this involves adding 3 variables, and in ANA our add instruction can only add 2 operands at a time and store the result in the third register operand. So we are going to have to break down this addition into 2 additions. So we'll say B is equal to A plus B, and then we will do B is equal to B plus C. So let's start that, and let's start with that. So we'll create label do. This indicates the beginning of the do while loop, and then we'll say add R3 R2 R3. So note that R3 is stores B, so this is same as saying B is equal to, and R2 stores A, so this is B is equal to A plus B. Next we want to do B is equal to B plus C, so we'll say add R3 R3 R4. So this is basically the same as saying B is equal to B plus C. For A plus plus, we'll simply use add I, and because A is in R2, we'll say add I R2 R2 1. So this is simply A is equal to A plus 1. Now for the loop condition, we need to check whether A is less than 5. So again, for comparison, we'll use subtraction. So let's use R6, which is another unused register, to compare the value of A with 5. So we'll say subtract R6, R5, R2. So this is basically the same as saying R6 is equal to 5 minus A. Now note that if R6 is greater than 0, it means A is less than 5. So we can simply say BGZ R6. If R6 is greater than 0, then we can jump back to this do loop. So we'll say ampersand do. So this ANA code is equivalent translation of the provided C++ code. The ANA translation of the previous C++ code is also provided over here. Now here are some questions from caches. These questions are directly lifted from the slide. They are essentially examples of the kind of questions you can get on the content present in the slides. So for instance, this question is asking us, what is temporal locality? Recall, the principle of temporal locality says that During execution, if a program accesses a certain memory location, it is more likely to re-access the same location as opposed to accessing some other random location. More generally, memory addresses that were accessed more recently are more likely to be accessed again than the memory addresses that were accessed a long time ago or never at all. Now here are some example scenarios where the principle of temporal locality is exhibited during program execution. So the first is loop execution. If you have a certain piece of code inside a loop, that piece of code would be accessed again and again until the loop repeats and executes. Similarly, if you have some popular global variables in the program or any functions that represent popularly used services, such functions and such variables are also going to express the principle of temporal locality. Alright, so to solve the problems on memory addressing, you again should remember the two important rules that we talked about in the class. So the first is using n bits, we can address 2 to the power n words or bytes. This is the first rule. And the second rule is to address m words or bytes, we need log to base 2 of m and ceiling of this number of bits. Okay, so we'll be using these two results to solve all these memory addressing problems, right? So the first problem here says that we are given an address of 39 bits and we have to figure out how much memory can be accessed using this. So again, recall, using 39 bits you can address 2 to the power 39 bytes, right? Because the problem tells us this is a byte addressable memory. So 2 to the power 39 is basically 2 to the power 9 multiplied by 2 to the power 30 bytes. So recall that 2 to the power 9 is 512 and 2 to the power 30 is actually giga, right? So this is 512 gigabytes. The second problem here is again as giving us a byte addressable memory, but the total size of the memory is given, it's 512 megabytes, and we need to figure out how many address bits would be needed. So now we will be using this second rule here because we are given the size of the memory. So 512 megabytes is basically 2 to the power 9, so 512 is 2 to the power 9 and mega is 2 to the power 20, so this is 2 to the power 9 into 2 to the power 20 bytes, which is 2 to the power 29 bytes. So to address 2 to the power 29 bytes, we basically need log to base 2 of 2 to the power 29 bits, right? So to address 2 to the power 29 bytes, log to base 2 of 2 to the power 29 and ceiling of this bits are needed. So which is basically 29 bits. So the third problem here, this is also a similar problem, but the difference is this is a word addressable memory where every word is 32 bits. And the question is how much memory can be addressed or accessed if the memory addresses are 39 bits. Okay, so once again, using 39 bits, 2 to the power 39 words can be addressed. Okay, now word size is 32 divided by 8, which is simply 4 bytes or 2 square bytes. Okay, so the memory size would be the number of words multiplied by the word size. Okay, so number of words is 2 to the power 39 and the word size is 2 square from here, so this is 2 to the power 41 bytes, which is basically 2 to the power 2 multiplied by 2 to the power 40 bytes. Recall that 2 to the power 40 is actually 1 tera. Okay, so this basically becomes 2 terabyte. The fourth problem here is again presenting us with a word addressable memory, but this size, the word size is 64 bits. And the question is how many address bits would be needed if we want to address 512 megabytes of memory. Okay, so first of all, word size is given by 64 divided by 8, which is simply 8 bytes, which is basically 2 cube bytes. 512 megabytes would be 2 to the power 9 multiplied by 2 to the power 20 bytes, which is 2 to the power 29 bytes. Now, how many address bits are needed? So to figure out how many address bits are needed, we first need to figure out how many words would there be in this total memory system, right? So the number of words would be given by memory size divided by word size. Okay, so that is basically memory size is 2 to the power 29 and the word size is 2 cube. So this is basically 2 to the power 26 words. So to address 2 to the power 26 words, we need log 2 base 2 of 2 to the power 26 ceiling of this number of bits. Okay, so this is basically simply 26 bits. Now this last problem on memory addressing is slightly different. So we again have a word addressable memory, but we are given the total size of the memory, and we also know, so the memory size is 2 gigabytes, and we also know that we have 28 bits in our addresses, but we don't know the word size. Okay, so let's find out the word size from here. So memory size is 2 gigabytes. So 2 gigabytes is basically 2 multiplied by 2 to the power 30 bytes, which is 2 to the power 31 bytes. Okay, now this is a word addressable memory. So using 28 bits, we can address 2 to the power 28 words. Okay, so we know the number of words, we know the memory size. So the word size would be given by memory size divided by the total number of words in the memory, right? So that is basically 2 to the power 31 bytes divided by 2 to the power 28 words. Okay, so basically this is simply 2 cube words, I'm sorry, 2 cube bytes. So that is basically 8 bytes. So this is associative cache that has only 4 cache lines. It uses LRU replacement policy. The memory addresses are 20 bits size, and it's a byte addressable memory. The block size is 256 bytes. What that means is every cache line can store 256 bytes. The question is how many bits are there in the block offset. So this is pretty straightforward. Recall that block offset, number of bits in block offset is basically log 2 base 2 of block size, right? So in this case we know that the block size is 256 bytes. So basically 256 is 2 to the power 8. So this implies basically block offset will have log 2 base 2 of 2 to the power 8, which is basically 8 bits. So the answer is also over here. So in the follow-up question over here, we are still given the same cache as on the previous slide. And what we have to do is, for these sequence of address accesses that is shown in the table over here, we have to figure out whether it results in a hit or a miss if we are using this cache described here, right? So this cache has 4 lines. Each line is 256 bytes, and it is a fully associative cache, right? So recall that if you have a fully associative cache, the memory address is going to be divided into 2 parts, right? You will have a block offset and a tag field. Okay, so the block offset is log 2 base 2 of block size, right? So and the remaining bits would be your tag field. So in this case the question says addresses are 20 bits, right? So and 256 byte is a block size, so the block offset will have log 2 base 2 of 2 to the power 8, which is 8 bits, right? Because 2 to the power 8 is 256, and the remaining bits in the tag field would be 20 minus 8, which is 12 bits. Okay, so this is first thing we should realize in solving this problem, the address division. So why is this useful? Recall. So let's start from here, right? Let's start from the top, right? So the first address, let's say this is your cache. Let's assume that there are, so the question said there are 4 lines, so the cache starts out empty, right? Now, so the first address is obviously going to be a miss. It cannot be hit, the cache was empty. So now the question is, in response to this miss, what addresses do you bring in, right? So we first have to break down this address into the tag and the block offset field, and then so basically the address is in hexadecimal, so this is hexadecimal 1 2 3 4 5, right? So each bit here, each digit basically represents a 4 bits, right? So this is 4 bits, this is 4 bits, this is 4 bits, and so forth, right? Every digit here is 4 bits. So the question is, so basically from the question we know that 8 bits is block offset, right? So basically these last 2 bits, this is your block offset, and this first 3 bits, this is your tag field. This is 12 bits, and this last 2 bits, this last 2 digits is 8 bits, right? So the tag is hexadecimal 1 2 3. Recall from our discussion, in a fully associative cache, whenever there is a miss, we will bring in everything that has this common tag, right? So basically the common tag hexadecimal 1 2 3 will belong to all the addresses in the range hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. Okay, so this is the key to solving the problem. You need to first figure out the address division, and then you have to figure out for every address miss, every cache miss, what range of addresses are brought in. Okay, so let's solve this problem here on the next slide. So this first access was a miss. Now let's say this is our cache over here, so let's create a cache, and it has 4 lines as given in the question. Each line is initially empty. Now in response to this miss, we have seen that this hexadecimal 1 2 3 4 5, this is your block offset, this is your tag. So in response to this miss, we'll bring in everything in the range hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. Okay, uh, so that let's assume that all of that goes into the top line over here, right? So here we'll have hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. So notice that the reason we are getting everything from 0 0 to FF is this least. So if you have this hexadecimal 1 2 3, and let's say we expand this least significant 8 bits, so everything that will have this common tag will be basically 0 0 0 0 0 0 0 0, right? It starts from here and goes all the way to 1 1 1 1 1 1 1 1, right? So this is basically in hexadecimal, this is hexadecimal 0 0, and this is hexadecimal FF. That's why we load this range of addresses. Okay, now just now we brought in this address range in the first line. So let's say, so here we have to keep the LRU information, right? Now because there are multiple lines, we cannot just keep 1 bit of LRU information. So let's say we mark a 1 in front of a line anytime it is accessed, right? And a 0 in front of all other lines. So 1 indicates access, 0 indicates no access. Okay, so the first one was a miss. Now the next address is hexadecimal 12397. Now is this going to be a hit or a miss? We have 12397. Notice that hexadecimal 123, we just search for the tag in the cache, right? So hexadecimal 123, this tag is present in the cache. Notice this is hexadecimal 123 starting from this. So everything with this tag is already present in the cache, so this is going to be a hit. Similarly, the next address is hexadecimal 12346, right? Once again, it has the same tag, so this is also going to be a hit. Next we have 23456, right? Now so hexadecimal 23456, now this tag 234, this is not present in the cache, right? The last 2 digits here, this is your block offset, so this is going to be a miss. Now also we forgot to maintain the LRU information, right? So for this next 2 accesses, these were also a hit on the first line, right? So we'll have 2 ones here and 2 zeros in front of the remaining rows. Okay, so the access information is important to maintain, as you'll see later on. So in response to this latest miss, hexadecimal 23456 will bring in everything in the range hexadecimal 23400 to 234 FF, right? Let's bring it in the second row over here. So we get everything hexadecimal 23400 to 234 FF here. We just now wrote in this row, so this we write a 1 here and 0 in front of all other rows. All right, So after this we have 23587. You see the tag is hexadecimal 235. Now this hexadecimal 235 tag is not present anywhere in the cache, so this is also going to be a miss. In response to this miss, in response to 235,887, we bring in everything in the range 23500 to 235FF, right? So let's use this third row here. So we get hexadecimal 23500 to 235FF here. So we just now wrote in the third row, so we'll mark a 1 here and a 0 in front of all other rows. Okay. Next we have hexadecimal 12289. Now you see tag 122 is not present in the cache. We have 123, 234 and 235. So this is also going to be a miss. And in response to this miss, we'll bring in everything in the range 12200 to 122FF, right? Let's bring it in the last row here, the last cache line. So we have 12200 to hexadecimal 122FF. We just now access the last row, so we'll mark a 1 here and a 0 in front of all other rows. Okay. Now after this we have hexadecimal 12357. So notice that 123 tag is present in the first line, so this will be a hit, and it hit in the first line, so this would be mark a 1 here and 0 in front of all of the lines. Okay, next we have hexadecimal 60000, right? So this tag 600, this is not present anywhere in the cache, right? So this is going to be a miss. Now the question is, in response to this, we know that we'll bring in everything in the range 60000 to 600FF, but the question is where, in which of these rows do we bring it in? So now we have to evict the cache, right? So we use Lru eviction. So let's find out which of these is the oldest cache line. Okay, so this line was accessed 1 cycle ago. This line, so this was accessed 1 cycle ago. This line was accessed 1, 2, 3, 4 cycles ago. This line was accessed 3 cycles ago, right? And this line was accessed 2 cycles ago. So notice that this is our Lru line. Okay, so we'll evict this data in this line. So we'll evict this data over here and bring in the new data here. So we'll bring in hexadecimal 60000. So and we just now brought in data in the second line, so we'll mark a 1 here and a 0 in front of all other rows. Okay, next we have hexadecimal 12289. So this is again a hit, it hits in this last line. Notice that 122 is present, this tag is present in the cache, so this is going to be a hit. It hit in the last line, so we mark a 1 here and 0 in front of all other lines. Next we have hexadecimal 23456. So the tag 234 is not present in the cache, right? We have 235, 122, 600 and 123, right? So this is going to be a miss. Now in response to this miss, again we have to evict something. So let's find out the Lru line, right? So the first line was accessed 3 cycles ago. This was the second line was accessed 2 cycles ago. The third line was accessed 1, 2, 3, 4, 5 cycles ago, and the last line was accessed just 1 cycle ago, right? So this is our Lru line. So we will now evict this line, the third line, and bring in the new data, hexadecimal 23400 to hexadecimal 234FF here. Now because we just now brought in the data in this third line, we mark a 1 here and a 0 in front of all other lines. Next we have hexadecimal 12399. So notice that the tag 123 is present here, so this is going to be a hit, and it hit in the first line, so we mark a 1 over there and a 0 in front of all other lines. Lastly we have hexadecimal 23587. Now 235 tag is not present right now, right? We have 123, 600, 234 and 122, right? So this is going to be a miss. And once again in response to this, we'll bring in data in the range 23500 to 235FF, and we'll have to evict the Lru line from here. So I hope you get the idea of how to solve this problem. The solution to the same problem